Today, we're jumping into a real-life physics detective story. It's all about how one incredibly tiny, almost insignificant measurement managed to completely flip our understanding of the universe on its head. It revealed that even the most empty space, well, it isn't empty at all.
And check this out. This quote is from the legendary physicist Freeman Dyson. This really tells you everything you need to know. What we're talking about wasn't some obscure little footnote in a textbook. It was the central obsession, the biggest mystery of its time. An entire generation of the world's most brilliant minds was captivated by this one tiny effect.
So here's the big question we're tackling. How did this happen? I mean, hydrogen is the simplest thing in the universe, right? It's just one proton and one electron. We really thought we had it completely figured out. But it turns out there was a tiny crack in our perfect theory. And pulling on that one little thread, well, it unraveled everything.
Okay, let's set the scene. The year is 1928, and the reigning champion of physics is the Dirac equation. And this wasn't just some run-of-the-mill theory. Oh no, this was a masterpiece. It beautifully stitched together quantum mechanics and Einstein's special relativity, and it made these absolutely stunning predictions about how the electron behaves.
Now here's one of its key predictions. The theory said, with no ambiguity, that for an electron in the second energy level, two different states, what we call the 2s and the 2p states, should have the exact same energy, perfectly identical, no difference whatsoever. The theory was crystal clear about this.
And right here, this is where we find the first clue in our mystery. On one side, you have the elegant, perfect prediction of the Dirac theory, total equality. But on the other side, you had these experiments popping up in the 1930s that kept hinting that maybe this wasn't true. The results weren't rock solid, but there was this persistent little whisper that something was wrong.
So this brings us to 1947, and this is where our lead detectives enter the scene, Willis Lamb and Robert Rutherford at Columbia University. They looked at this confusing picture and decided, you know what, we are going to settle this once and for all, using a brilliant, brand new experimental technique.
Their method was just genius. What they did was they'd zap these hydrogen atoms with microwaves. Now, if they got the microwave frequency just right, it would give the atoms in that long-lived 2s state just enough of a kick to flip them into the short-lived 2p state. And because that state is so short-lived, those atoms would decay before they even reached the detector. So what you'd see is a sudden dip in the electrical current. It was an unbelievably clever way to measure that tiny energy gap with incredible precision.
And this was the answer. 1057 megahertz. Remember, the best theory in the world predicted zero. Zilch. But Lamb and Rutherford found this tiny, undeniable gap. The 2s state had just a little bit more energy than the 2p state. That crack in the theory, it was now a confirmed, undeniable fracture.
Now, let's be real. This is a minuscule amount of energy. But when Lamb stood up and presented this result at the legendary Shelter Island Conference in 1947, it sent a complete shockwave through the room. The theory, their perfect, beautiful theory, was definitively wrong. And now, they had to figure out why.
So what in the world could be causing this? A tiny energy shift in the simplest atom in the universe? The answer didn't come from the atom itself. Nope, it came from the supposedly empty space all around it. And the explanation, to put it mildly, was just bizarre. You see, it turns out that the quantum vacuum, the empty space we think of, isn't empty at all. It's this roiling, bubbling sea of energy where pairs of virtual particles, like an electron and its antimatter twin, a positron, are constantly popping into existence and then annihilating each other in a flash. This is happening everywhere, all the time. Empty space is not nothing. It is a chaotic hive of activity.
Okay, so picture the hydrogen electron orbiting the proton. It's not a smooth ride. It's constantly being buffeted and knocked around by all these virtual particles popping in and out of existence. All this action makes the electron jiggle and vibrate, and that motion effectively smears out its position. It's no longer a perfect little point, but more like a tiny, fuzzy cloud.
So why does this smearing matter? Well, it all comes down to location, location, location. An s-state electron actually has a pretty good chance of being found right at the nucleus. A p-state electron, on the other hand, is never there. And since the s-state electron spends more time in that chaotic central region, it gets jiggled around a lot more. This jiggling effectively weakens its connection to the nucleus, pushing its energy level up just a tiny, tiny bit more than the p-state. And that tiny push, that is the Lamb shift.
So, there you have it. Lamb and Rutherford found the shift, and this wild idea of vacuum fluctuations explained it. But this was so much bigger than just solving one little puzzle. This discovery basically forced a complete and total overhaul of modern physics. You have to understand, before the Lamb shift, quantum theories were kind of a mess. Whenever physicists tried to actually calculate the effects of things like these vacuum fluctuations, their equations would just break and spit out the answer infinity, which of course is completely useless. The Lamb shift was the crucial piece of experimental proof that showed a radical new idea called renormalization was actually correct. It was a mathematical trick that let them finally tame those infinities and get real, finite answers.
And this discovery just lit a fire under the entire physics community. I mean, the story goes that Hans Bethe did the first rough calculation of the shift on the back of a napkin during the train ride home from the conference, and his answer was amazingly close. Soon after, giants like Feynman, Schwinger, and Tominaga took that insight and built it into the complete theory of quantum electrodynamics, QED, which to this day is one of the most successful and precise theories in all of science.
So that was all way back in the 1940s. Why are we still talking about this? Well, because the Lamb shift went from being this nagging problem that needed to be solved to being one of our most powerful tools for peering into the unknown.
Today, scientists are still measuring the Lamb shift, but with unbelievable precision, trying to find any tiny deviation that might hint that our best theory, QED, isn't the final word. They use it in exotic atoms to measure the exact size of the proton. They even compare it in matter versus antimatter, looking for the slightest difference that can unlock new secrets of the universe. It's become a magnifying glass for finding new physics.
And that just brings us full circle, doesn't it? The Lamb shift proved, beyond a shadow of a doubt, that nothing is actually something. It completely changed our picture of empty space, from this quiet, boring void into a dynamic, seething foam of quantum activity. And it leaves us with this really incredible question. If one tiny, unexpected shift revealed all of this, what other profound secrets are still hiding out there in the vacuum, just waiting for the next experiment to bring them into the light?